You remember a normal subgroup, right? A normal subgroup. Okay. What's the difference? So let G be a group and H a subgroup of G. Okay. Then the normalizer of H in G. So we write the normal subgroup are elements that commute with all other elements in the group, right? The normal subgroup of G is X in G. XG is GX for all G in G. Okay, so the normal subgroup is all elements that commute with all other elements in G. The normalizer is a subgroup. It's a subgroup of G. Its elements is a set of elements that commute with this subgroup H. Okay, what if now you're thinking about all the subgroup, right? You're thinking about all the subgroup in a group. Okay. My question is, what is NG of E? If H is E, NG of H is equal to, what are elements of G that commute with this? All. It has to be all because everything commute. So this is equal to G. Okay? Number 2. If G is abelian, okay? If G is abelian, what is NG of H? And H is a subgroup of G. Okay? This is also equal to G because all elements in G will commute with elements in H. G abelian, H has to be also abelian. Okay? So what commute with all elements in H is all, right? Because it's abelian. So these are, okay? You can go through to see what is a subgroup. Why E is inside? Why E is inside? Because EH is HE, right? So E is inside. Second one, test of subgroup. It has to be closed, right? So if G1, G2 in here, why is it G1 times G2 also in there? Claim. Why is it a subgroup? Okay, why is it a subgroup? And G is a subgroup of G since number 1. E of
Sorry,
G.
proof. If we put instead of GH equal HG in the condition such that GH equal HG, instead of this, if we use G inverse equal H is the same or no?
So GH is HG.
Yeah, because
G
this is uh,
H is
well
H.
H. So this is the assignment number 6. No, because of that I asked this question.
Assignment number 6 in this group, in this
No,
chapter,
no.
different chapter. Chapter 10.
Question number 5. Yeah, exercise.
Oh, okay.
Uh,
So it's assignment. Assignment I cannot answer. This has something very close to being in the normal, right? A normal subgroup. And left and right cosets are the same, right? So this is exactly how you relate. Yeah, you can do this or you can do this. And the test that we did last time, you can just show to find like the normal one, right? Okay, so if you put EG, is it in NG, right? Since, is it inside? Since EH is H. HE also H. So EH is HE is, that is the identity. Okay. If you use this one, you will get E inverse HE is EHE is also H. The same thing. Next is the second one is close, right? Subgroup test and then inverse. G1, G2 in NGH. G1, G2 in GH. So G1, G2 in NGH means G1H is HG1, G2H is HG. Now, is it inside? So we try G1, G2H. This is by definition. This is G1H, G2H, which is, I'm giving you the answer for the assignment. You, right? So third one, inverse, I think you can do it. It's the inverse. Just bring the other side. Okay, so it is a subgroup. That is normalizer. Okay. I give that example of S3. Okay, there is example 7.6 is the example for S3. Okay, you can just multiply and see whether to find which element that it has something to do with the coset also. So if I give you H, I will give you the non-abelian group. If it's a abelian group, then it's the whole group. Okay. So if I give you a question to find the normalizer, then you have to find G in which GH is HG. Okay, and identity has to be in there. Identity is always in there. Okay, the other one is a centralizer. Oh, this is easy. It's the same thing. Okay. So I use CGH, right? CGH. Okay. Now the thing is to that particular
H.
it's the particular element. Okay, just now you can multiply to the set and get the set back in terms of multiplying the element. So it can be a different H. This one is that particular H. You want to see GH is HG for that particular one element. So that's the centralizer of H. Okay. So you see, if H is just one element, right? If H is just one element, the normalizer and the centralizer is the same. Because you multiply by the element or you multiply by the set is the element. It's just only that one. Okay. And if H has more than one, why Tan is coming in and out? Tan is living on campus. Okay, if, what is this in my pocket?
Different.
If the order of H bigger than 1, okay, then CG of H is not necessarily equal to normalizer. Okay, so they can be different. So it depends. You have to see. Okay, let's try to find the normalizer, or this one you find the centralizer of the rotation in D4. The normalizer or the centralizer? The centralizer. Okay, so you can try with an example and see. You have to find a non-abelian group, yeah? Find a non-abelian group. What is good about the smallest non-abelian group is the computation is not that difficult. So, homework, yeah? Let G is S3 and H1 is this, H2 is this. Find the normalizer of H1, the normalizer of H2, the centralizer of H1, the centralizer of H2. On Monday, I will want to see this. Okay, And please type so you can share the screen. If you don't type, make sure you take photos so you can share the screen. Okay, so this is for Monday. Four of you can show the screen. Share the screen. Show the screen. Okay, who asked me about this just now? Amtinan?
Me, yeah.
Okay. Cannot unmute. All right. So we'll continue with the. Okay, let me go to whatever I want to go. In the beginning, which is ideal. Yeah. Ideal of a ring. Anything else? If I miss and you don't understand, I can go back and you can let me know. Okay. All right. So before we go to ideal, we go to left ideal and right ideal. Okay. Let R be a ring. And I is a subset of R. I is not empty. Some ideals sometimes they use the not addition. So it's a bit. Okay, then I is called it. Then I is called the left ideal of R if for all A, B in I, okay, A minus B is also in I, and RA is in I for all R in I. And the fact that we call it a left ideal because we multiply the element of the ring on the left. Okay, and the same thing with the right ideal. It's called the right ideal. We don't change this, but if AR is in I for the right ideal. Okay. Then if they are both left and right ideal, I is an ideal if I is both left and right ideal. Meaning RA is in I, AR is also in I. Okay, question. What if the ring is commutative? If the ring is commutative, these are actually equal. Okay, if the ring is commutative, you don't have to show both because they are equal. So if it's left, then it's also right if the ring is commutative. But you have to look what is your I. In the beginning, I is a subset. So you have to check. If you were given the big R and you're given the I, you want to check whether it's an ideal or not, you have to check these two conditions. Okay? Okay, now there is an example. Let's go to the example. I don't want to erase, but I erase. Let R be 2 by 2 matrices. Seriously, need to edit this. And to Z is I don't know the one that maybe Hannah already update that, but what is it in there? The Z is a Z or yeah, okay. So another one. And let I1, okay, A0, B0, A, B in Z. It's a subset, right? This is 2 by 2 matrices with integer entries. This is also, but this is specifically A0, B0, right? It's a subset. And I2 is the other way around, 0A, 0B. Okay. Oh, ada I3. That's I3. Okay, A, B, C, D. Okay, I think my normally I put this like this. A, B, C, D. A, B, C, D, and Z. Okay, and this one, it doesn't matter. I can put A, B, C, D too, but A, B, C, D in 2Z. Even integers. And I have 4. Just one there. Okay, just one here. Okay. Now first, they cannot be empty. Okay, they cannot be empty. You can put any number, any integer, even when A, B, 0, right? So the ring has, a ring is an abelian group, okay? So 0, 0, 0, 0 is in all of them. So first is not empty, okay? Next is what happened when you minus, right? So you take 2 integer and you take another one and then you subtract one from another. Okay, A1 0, B1 0 minus A2 0, B2 0 is also integer, right? Okay. The next one is you have to multiply by any ring and see whether it's in I or not. Okay, this is the easy one. This one also. When you minus, still integer. Okay, integer is okay. If you change this to somehow maybe positive integer, then you take the subtraction, positive integer, like 3 and 7, 3 minus 7 is not anymore positive. Okay, so that one you have to look. Now you multiply, right? Left, R times A. So the R is the A, B, C, D. Or now you cannot use A, B, C, D because there's already A, B. So here I use X, Y, Z, W. xy z w times a0 b0 xa plus by 0 az plus bw 0. And this is again in I1. So it's a left ideal. Okay. Try to multiply on the right. Try to multiply on the right. So I multiply on the right. X, Y, Z, W. I get AX, AY, right? BX, BY. This is not in I1 because this is not 0. So it is not the right ideal. Okay, it is only left ideal, it's not the right ideal. Then you can check the rest. Similarly, I2 is not right, but left. Okay, this one the same thing. Okay, left but not right. Okay, I3 is an ideal. You have to multiply, write it out. This is an ideal because this is just exactly inside, right? Then you multiply left and right, it's okay. I4 is not an ideal. I4. Again, you multiply left and right and see it's not like this. So try with A0, 0, 0, right? Okay, what happened? AX, AY, 0, 0. So this is not in I. Okay, so that is ideal. The collection of the intersection of the right ideals will give the right ideals. The intersection of the left ideal is also a left ideal. Okay. All right. Now, if we have an ideal, then we have a quotient ring. You remember when we have a normal subgroup, then we have a quotient group, quotient or factor group. The same thing for ring. If you have an ideal I, then that is how we get a quotient ring. Let R be a ring and I is an ideal. Left and right. And R mod I with, sometimes I use dot, sometimes I use cross for multiplication. Is called the quotient ring of R by okay. And we also have a ring homomorphism, like isomorphism theorem using isomorphism. Okay. And for the ring homomorphism is if you have two rings and the function from one ring to another ring is a homomorphism if you have both. You remember when we do this for homomorphism for groups? Only this, right? For groups. Now for ring, you have both. So this is ring homomorphism. You remember when we do about morphism, when I mentioned about the isomorphism, I remember our class is from my home. I remember I asked you to find so many words that have morphism, right? So we have homomorphism, and then we wrote monomorphism, the same thing here. Epimorphism if it is onto, and isomorphism if it is one-to-one and onto. Okay, I think, okay. Last one is kernel, yeah? Kernel is, you learn this in linear algebra, right? Kernel of a homomorphism. It's the same thing here. It's defined the same thing. Kernel of a homomorphism. Okay, isomorphism theorem, I will bring it to next semester. Hopefully next semester is physical. Okay, all right. So, although you can try and start do the exercise 11, as I mentioned, for now, okay, let's do your Venn diagram first, okay? And then I will decide whether I need to see your proof, because this one is in the final, okay? This is in the final. Sometimes why do I need to ask you to send assignment? I want to see how you actually write the solution, okay? Whether you really understand or not. Okay, so Monday I will start with group presentation, but the class will start from your presentation. Before I present the group presentation of the last chapter, you will present, not group not, that is group presentation also, right? I'm confused. There will be two different set of group presentation. One is group presentation just now. No, right? No, now I'm confusing myself. Forget it, erase. Okay. What did I ask you to do for next class? Okay. Empty none, because I don't see your face, that's why. Blame on empty none. So in the next class, okay, it's like erase. Okay, go back. In the next class, you will present about normalizer and centralizer, not group presentation, okay? So try to write out. If you don't have time to type, just take photo, then you can share. Okay. So normalizer and no, just normalizer and centralizer. The one I gave you for S3, right? And then I will go into the new chapter of group presentation. My presentation on group presentation. All right, okay. I'm making myself confused, and everyone else is like, what is this, Poniza? It's already like almost 4:30 late afternoon. And okay, any question before we stop the class? Wally, okay?
Proof,
You look
mat-
so cold, Wally. Is it cold? Ahmad, you look so serious. It's like
I have blood pressure.
what is it?
Blood pressure.
Okay. Okay, let's
Proof,
take one.
can you multiply these 3 cycles?
Can I multiply?
I gave you a 3 cycle. Just
3 cycle?
yeah, I confused of multiplying
Oh,
this.
give me the 3 cycle. Where is
One.
Suddenly, like you put it back because you don't want it to Jatuh and then you forget. Okay, 1.
1 to 4 is one cycle. Another one is 1 2. Another one is 1 4 2. This one.
When I do my multiplication, I do it from the right. Okay, you go from the
Okay.
right, and I will start from the smallest number.
Hmm.
Smallest number. 1. So you have to go from one cycle to another until the end. 1 goes to
4.
4 goes to 4 because you don't see. 4 goes to,
1.
or you can go 1 to 4, 4 to 1. Then you close. Then you start with 2. 2 goes to 1. 1 goes to 2. 2 goes to 4. So 2 goes to 1. 1 goes to 2. 2 goes to 4. So you stop.
1 goes to 2, 2 goes to 1. Is the cycle is not closed?
Which one? This one or this one?
The second one. 2 goes
This
to
one?
4.
Not yet. I have not finished.
Oh.
2, right? 2, right? 2.
Hmm.
2 goes to
Yes.
1.
Yes.
1 goes to.
1 goes to 2. The cycle is not closed here.
No, you haven't finished. There's another one that you have to multiply.
Okay, okay. The
2,
problem.
you have to go until the left.
Hmm.
Now 4. 4 goes to 2. 2 to 1. 1 to 2. Then you close. So don't
Okay,
stop here. You
understand.
have to go until way.
Hmm. Okay. Yes.
Okay. Okay.